Hello and welcome to this recorded learning module for ASIC designers targeting Xilinx programmable FPGAs. My name is Frank Nelson. I am a Xilinx technical trainer and a course developer. I'll be your instructor for this module. This module is a comparison of FPGA and ASIC technologies. Each module in the ASIC to FPGA series provides an overview of differences, advantages, and disadvantages between ASICs and FPGAs. The first module in this series, FPGA and ASIC Technology Comparison, contrasts the technological differences of ASICs and FPGAs. If you're an experienced ASIC designer transitioning to FPGAs, this course will help you reduce your learning curve by leveraging your ASIC experience. Careful attention to how FPGAs are different than ASICs will help you create a fast and reliable FPGA design. After completing this module, you will be able to describe the differences between ASIC and FPGA architectures. After hearing other modules, you will be able to understand how these differences will affect your design's HDL coding style, implementation, product selection, and system performance. First, we're going to take a look at some of the general differences between the ASIC and FPGA architectures. Then we will look at some of the fundamental considerations for selecting devices, cost pressures, the size of the device, performance characteristics, typical volume, analog circuitry if necessary, time to market pressures, and the capability to reprogram the device. All of these factors decide whether an FPGA or an ASIC is used. Some customers still try to choose an FPGA by using a gate counting methodology. This is an inefficient process. We recommend building a sample design and just resynthesizing it for your chosen device family. Of course, you should use good HDL coding practices for optimum results. In general, gate counting methodologies for ASICs require extra gates for registers that are included with FPGAs. So choosing an FPGA by gates is often very misleading. It is also useful for you to know that clocking structures for ASICs allow you to have pretty much anything functionality you want, while FPGAs give you a DCM and a PLL and don't allow all frequency combinations. So FPGAs are a bit more restrictive when it comes to these clocking structures. As you will see in a few slides, another major difference is configuration. FPGAs are SRAM-based devices, so they need to be reprogrammed upon power up. This requires that customers design a place to store the bit stream of the FPGA in their system. Some customers plan on adding a flash or an SD-RAM component into the system to accommodate this. However, this is not necessary for ASICs. A significant benefit, as you might already know, for configuration is that the FPGA can be reprogrammed many times. This is significant since the user gets plenty of opportunities to fix any design problem they might have. Power consumption in the FPGA industry has improved significantly as these devices have shrunk and become more power efficient. This enables FPGAs to be used in many more applications than ever. Well, first we're going to cover standard cells, also commonly referred to as a custom ASIC. Some advantages that ASICs have are that they simply have the lowest price for a high-volume production device. This is their biggest advantage and is the benefit of their technology. However, being the latest and greatest technology, which usually gives them the biggest size and speed advantage over other devices, they charge a premium. They also support some of the fastest clock frequencies, offer the largest densities in the industry, have the capability of having integrated analog functions, and consume the lowest power. Some disadvantages of standard cell ASICs are that they have the highest non-recurring engineering cost, or NRE, and the longest design cycle, which makes it critical that the design is built correctly the first time. Generally, there is limited vendor intellectual property, or IP, and it often has a high cost of development. These ASICs have the highest cost for engineering change orders since they require an extensive amount of time to verify. The ASIC verification time is longer since a more thorough verification of the ASIC's performance is needed to ensure functionality. Bottom line, testing is critical for ASICs since the cost associated with a respin is prohibitive. Likewise, the tools required for design and test are more expensive than FPGA tools. Often a vendor will not differentiate between a custom ASIC and an embedded array. Embedded arrays are generally a more mature process technology than a cutting-edge custom ASIC. An embedded array has some advantages. Low price for medium to high volume production. Performance is only slightly slower than a standard cell ASIC. They support many gates. In fact, a 50 million gate device will allow some custom macros. They are also generally more flexible than an FPGA and use less power than FPGAs. Some disadvantages of embedded arrays include a high non-recurring engineering cost, a longer design cycle than an FPGA, again limited vendor IP with a high cost associated with that, and generally they implement digital circuits only. But in general, they require extensive testing, have similar caveats, and have as much design risk as standard cell ASICs. A Xilinx FPGA or Field-Programmable Gate Array has some significant advantages over ASICs. FPGAs have the lowest cost for low to medium volume production, although Spartan 3A devices are specifically targeted towards high volume, low cost ASIC applications. As with all Xilinx FPGAs, there are no non-recurring engineering costs associated with them. FPGAs are a standard, off-the-shelf product that offers the fastest time to market. Xilinx provides an extensive library of IP as part of its core generator. Most of this IP is free except for only the most sophisticated technologies. Likewise, the Xilinx core generator offers IP that has been made by other experienced Xilinx FPGA designers that are not affiliated with Xilinx. These cores have a charge associated with them, but they are inexpensive compared to ASIC vendor IP. Using Xilinx IP allows IP updates to be integrated into the design without the cost of a mask or a respin. This is helpful if you are using an emerging standard while the standard continues to be enhanced. This enables designers to adopt new standards early without the risk of a standard changing and then making your ASIC obsolete. FPGAs enable bug fixes to be made quickly and inexpensively since they are SRAM-based and reprogrammable. This also gives FPGAs the ability to be upgraded or enhanced in the future without the cost of a mask respin. FPGAs do have some disadvantages, however. FPGAs run slower than ASICs, but the newest FPGA family, Virtex 5, can run as high as 550 MHz. The size of the largest Virtex 5 device is limited to around 25 million system gates. FPGAs are entirely digital, except for the embedded PLL that is part of the clocking resources. Xilinx FPGAs are SRAM-based, using a 65 nanometer copper CMOS process. Generally, the largest FPGA today can accommodate approximately 25 million system gates, including the RAM, logic gates, and I/O resources. Virtex 5 devices can run at up to 550 MHz. The ASIC Design Suite with integrated synthesis and place and route tools can be purchased for approximately $2,500. That does not include the optional hardware simulator, I might add. The ASIC Design Suite can be used on both PC and Unix machines. FPGA tools are very inexpensive when compared to ASIC tool sets, which would probably cost a lot more. Note that most experienced customers use a third-party hardware simulation tool to test their FPGA design. This is strongly recommended and is not included. Likewise, many Xilinx customers use our integrated logic analyzer, ChipScope. This is also an additional software suite. Each of Xilinx's tool sets is available on a trial basis. This includes the ISE Webpack, which supports most of Xilinx's devices and is entirely free for life. While the Webpack does not include all of Xilinx's tools, it is very suitable for many customers. Configuration must occur on power-up, but can also occur on demand. This is done by toggling the FPGA's programming pin. FPGAs must be configured because their SRAM cells are volatile. The user will have to plan on storing their configuration data, commonly called a bit stream, in a PROM, an SDRAM, or some other external data source. This, of course, will cause some additional cost to your final system. To build your system, you'll have to understand the basic configuration process and how to set up various configuration modes and daisy chains. But before you can get to that point, you will need to understand the advantages and disadvantages of each configuration mode so you can choose the appropriate one for your system. You may also need to gain some knowledge of how a series of FPGAs can be daisy-chained to use a single memory source, just in case your system requires multiple FPGAs. As was mentioned earlier, reconfiguration of the FPGA allows the device to be modified, fixed, or the design upgraded without wasting the device. This extends the life of the product a great deal. But most importantly, it enables a faster development time to our customers. Instead of lengthy development times, they can simply make the design change and program the same device. There have also been plenty of applications where a single FPGA was reprogrammed in system with a different bit stream to enable the FPGA to serve multiple purposes at different times. This has given way to the concept of partial reconfiguration. Partial reconfiguration allows part of an FPGA to be reprogrammed actively while the device is operating. To illustrate, take a laser printer. You could build a controller as part of the FPGA design and have a series of buffers that are reprogrammed actively, based on the font or paper size the user selected. Now this might allow a smaller FPGA to be used since the buffer could be reprogrammed quickly from an external memory source, and only the buffer that was needed at the time would have to be programmed into the FPGA. While partial reconfiguration is a very cutting-edge technology, it is not necessarily suitable for many customers. It is fascinating, and hopefully this example gives you an idea of what partial reconfiguration means. There are lots of configuration modes you can choose from. They are all equally valuable and allow our customers to choose a configuration scheme that is right for their application. First, users should always consider configuring their device via a Xilinx download cable. These cables allow the user to reconfigure their FPGA with only a download cable on their computer. The configuration modes that use these cables are used primarily for prototyping and debugging. These cables are low cost and are typically used to configure the FPGA in a JTAG configuration mode. Configuration can also occur with the use of a microprocessor or microcontroller. These configuration schemes involve some other external control logic being used to control the configuration process. In these configuration modes, the FPGA is a slave to whatever control logic is managing the configuration. These configuration schemes require extra components and thus have added cost associated with them. Most users consider this configuration scheme if they already have the external control logic available as part of their system. Configuration can also be completed using the Xilinx Platform Flash PROM. These configuration schemes usually use the FPGA's built-in configuration logic to control the FPGA's configuration. With these components, the FPGA usually configures itself. These configuration schemes require the user to buy a PROM, which has some additional cost, but these configuration schemes are usually the easiest to debug since the control logic is already fixed as part of the FPGA. We will talk about the Xilinx Platform Flash product in the Basic FPGA Configuration 2 module. Some new configuration options have just become available to Xilinx users. The Serial Peripheral Interface, SPI, and the Byte-Wide Peripheral Interface, BPI configuration schemes allow users to purchase off-the-shelf commodity flash components. The flash memory can then be used to store the configuration bit stream and for the user's application memory, if the user is building an embedded system. Note that to this point we have discussed having only one configuration mode. In reality, most customers want to debug their prototype and then later program the FPGA with a different configuration scheme. To do this, most designers build some simple control logic which will allow the system to switch between the 2 or 3 configuration schemes of choice. Alright, so let's take a look at the basic architecture of Xilinx FPGAs. The first and most significant resource is the CLB, or Configurable Logic Block. The CLB contains registers and LUTs, commonly called lookup tables. The LUT is your primary combinatorial logic resource. We'll discuss the LUT and the contents of the CLB further in the next couple of slides. Throughout the FPGA are columns of block RAM, DSP slices, and other dedicated hardware. This includes PCI cores, eMAC blocks, perhaps a PowerPC processor, and other dedicated resources. Since the type and quantity of dedicated hardware will vary by product family and density, it is a good idea for you to flip through the datasheet to help you decide which device family is right for your application. IOBs, or input and output blocks, contain registers and other specialized resources that are designed to help interface signals to the outside world. Every input and output signal in the design must go through an IOB. The IOBs also have a programmable I/O standard functionality that supports up to 40 different I/O standards. So each pin has a programmable interface that is programmable on a pin-by-pin basis. Outside of the CLBs are large arrays of routing resources. The routing is connected together with switch matrices. The switch matrix allows many different lengths of interconnect to connect a signal from any source in the FPGA to any destination. This structure is designed to assure routing flexibility so that all designs can route to completion. It is also designed to assure short routing delays so that system performance objectives can be obtained. To aid the software in the effort of obtaining desired performance, Xilinx supports the use of timing constraints through its ISE design suite. Timing constraints allow designers to specify their desired timing objectives, which the tools will then use to guide the placement of logic and the assignment of routing. Another significant resource is the clocking resources. Vertex 5 includes DCM, or digital clock managers, and PLLs, or phase lock loops. They also have dedicated routing resources that are used for the distribution of clock signals with minimal skew. DCMs are used for clock signal generation, while PLLs are primarily used for the removal of clock jitter. The logic cell is considered a standard benchmark in the FPGA industry. Each logic cell is essentially a single LUT with an associated register and is considered the fundamental building block of your design. As we have already mentioned, each Xilinx device contains an array of CLBs. Each Vertex 5 CLB has 2 slices. Each slice has 4 LUTs and 4 flip-flops. Basically, this diagram is replicated 4 times to make a single slice. That means that each Vertex 5 CLB has 8 slices. Now, this is not very important. It just makes comparison of devices and device families a little easier if you speak our language. Now, combinatorial logic is implemented with a LUT. Each LUT can implement any 6-input combinatorial function of your choosing with a constant delay. So you quickly realize that the complexity of the combinatorial function does not matter as long as the function does not require more than 6 input signals. Now, the flip-flop can be programmed as a latch, although that is not recommended, a JK, an SR, a D, or a T-type flip-flop. The actual flop is a D-type that's used in the silicon, so extra gates are used to convert it to a desired type if you choose to use something other than a D-type flop. These gates are just merged into the associated lookup tables. The slice also includes arithmetic logic implemented using the carry chain. Carry logic is used for the implementation of fast arithmetic functions such as adders, accumulators, subtractors, etc. The carry chain enables the fast propagation of carry signals to the next bit and/or slice. This improves the speed of the function, saves general routing resources, and also saves LUTs, since the combination of the LUT and the carry logic implements a sum and a carry output. Combinatorial logic implemented in the LUT is implemented basically by converting the gate-level combinatorial logic into a truth table. LUTs map the combinatorial logic into a truth table and then basically use the table as a ROM. So a LUT is basically a 64 by 1 ROM. By mapping the logic, which means optimizing the inputs versus the combinatorial logic function, into the output Z, we have a very simple method by which to implement combinatorial logic. While synthesis tools will optimize your combinatorial logic, one of the essential things they must do is map the combinatorial logic to the 6-input LUT. This is essential because a function of, say, 7 inputs might require a second LUT, and if optimized improperly, might add a LUT in series. This, of course, would increase the combinatorial logic delay and frequently impact system speed. Notice that the LUT is limited by the number of inputs and outputs, not by the complexity of the logic. In other words, we could implement a simple inverter, or we could implement a 2-input AND gate, or we could build any single output function of up to 6 inputs. For wider input functions, the outputs of 2 LUTs within a slice can be combined to make larger combinatorial functions, such as a large mux. In this case, a 13-input function of limited functionality can be made. The beauty of this resource is that it saves extra LUTs from being cascaded in series, which, as I mentioned earlier, will likely hinder system performance. Now, this resource also saves LUTs from being used to cascade logic and instead uses the dedicated muxing structures. These hardware resources are very fast, especially the routing, which is dedicated in the device for just this purpose. Your synthesis tool should infer this resource whenever necessary, but it might depend on your HDL coding style. For example, you might need to use a case statement. LUT-based memory is referred to as distributed RAM or distributed ROM. Recall that our FPGA process uses SRAM technology, so the LUT is fundamentally a ROM. Now we can implement this by activating the configuration write strobe. So this is the write strobe that's used during the configuration of the FPGA to make the lookup table function as a piece of combinatorial logic. But by activating that configuration write strobe, we can actually use it as a little 64x1 RAM. Likewise, the core generator can combine multiple LUTs for larger memories that are deeper and or wider. You should remember, however, that each of our devices have dedicated block RAM, so don't get too carried away with this functionality built into the LUT. It is really only intended for small memories. In fact, 128x8 memory sizes are very common. Also note that the 6-input LUT architecture has 2 5-input LUTs, which add more flexibility to your design. The carry logic is a dedicated resource for propagating carry signals. This consists of a couple dedicated multiplexers, an XOR gate, as well as the LUT to implement a simple carry chain. Remember, this is dedicated, so it saves LUTs from being used to build this chain, and it is also very fast. The way to access this resource is by using an arithmetic operator in your HDL code, so the synthesis tool can infer the carry logic resource. The memory blocks, also known as block RAM, support single and dual port synchronous operations. In dual port mode, these block RAMs support fully independent port functionality for both read and write. Notice on the diagram we have 2 ports, the A port and the B port, with fully independent clocks, write enables, output enables, address, and data. Also note that there are separate outputs, data A and data B. Sizes up to 36 kilobits can be configured using a single block. However, this architecture allows it to be segmented into 2 independent 18 kilobit memories, if desired. Note that there is an available parity bit option as well. Vertex 5 also has dedicated cascade logic that allowed 2 block RAMs to be configured as a 72 kilobit memory. While these blocks of memory are generally spread out across the die in columns, this feature allows for larger memories to be made and enables higher performance. Also note that these block RAMs have dedicated FIFO logic associated with each block, so high performance FIFOs can be made without using any extra CLB logic. This table shows you the available memory configurations for each port. As you can see, some of the larger sizes support the parity bits without extra CLB logic. Note the various sizes of the output ports. Also, keep in mind, if you need a smaller port memory, you just don't connect the unused bits. One of the most useful features is that each port is entirely separate, independent, and configurable. So in this example, the input bus of 8 bits is stored in the block RAM, yet an output data is taken out in 32-bit chunks. The data width conversion is done automatically and without extra logic. On a side note, most customers use the Xilinx core generator to build custom memories, like the one that is described here. The IOB, commonly called an input and output block, consists of registers for clocking in or clocking out data. As you can see in this diagram, there are separate registers for this purpose. This allows the IOB to be configured for bidirectional I/O paths as well. Each IOB also includes a 3-state enable register to enable double data rate applications, but this is not shown. But all these features are, of course, optional. Note, each input and output path can be combinatorial or registered. While this is optional, experienced designers recognize the significant benefits of always registering the input paths to the FPGA and likewise registering their output paths. This allows for improved system speed and better design reliability. Each register can have a separate clock and clock-enabled signal, but the set and the reset signals must be shared between these registers. This is important since your HDL coding style will have to reflect this behavior if your synthesis tool is going to infer the IOB registers. This is necessary because these registers are considered separate from the CLB registers. Included with each IOB is the ability to select each I/O pin with a different I/O standard. The default I/O standard will vary by device family because each device is built at a different technology. Each pin also supports a programmable slew rate. Slow slew rate is the default, and careful use of fast slew rate is always recommended because it makes the design more susceptible to ground bounce. For more information about the supported I/O standards, please refer to your device's datasheet. Also included is the built-in SerDes logic. These resources are not incorporated with every IOB, so take the time to plan the layout of pins that will be using the SerDes functionality. To find out which pins include the SerDes circuitry, refer to the device datasheet. The SerDes circuitry can be programmed as input or output. The I-SerDes allows the user to divide by up to 10, while the O-SerDes supports multiplication by up to 10. Another dedicated hardware resource that is frequently used is the DSP Slice. This resource is designed to build large arithmetic functions typical of DSP applications that run at a very high speed. As you can see from this slide, it contains a dedicated hardware multiplier capable of a 25 by 18 multiplication. It also contains a large programmable accumulator that is capable of subtraction and other functions. This enables other functionality like pattern detection. This block also has a separate C input that can be used for loading values into the DSP Slice. Additionally, there is a dedicated cascade chain that enables the creation of even larger arithmetic and DSP function. This feature also enables a wide variety of filters to be implemented. For constructing components with these resources, we recommend using the core generator. This will allow you to quickly learn what components are already supported by the DSP Slice and can be easily generated. The routing structure throughout the device is a combination of both programmable and dedicated routing lines. Global clock routing resources are built into all of our FPGAs with a predefined clock tree. This assures global routing with minimal skew that is separate of general routing resources. You should also note that some secondary control signals can be routed on the global routing resources as well. This is sometimes necessary if a clock enable or a reset has a very high fan-out. There are also regional clock routing resources that enable local routing of low fan-out control signals into specific regions of the device. The dedicated I/O clock global low skew routing resources are used for distribution of SerDes clock signals. This is helpful since these clocks are always routed to neighboring I/O pins. Also included in this category is the carry chain routing and the dedicated routing for block RAM and DSP Slice resources. General routing resources, as I mentioned earlier, are used for transmitting data signals between CLBs and IOBs and switch matrices. Clock management resources include a series of dedicated clock trees, which are pre-optimized clock networks that balance the skew and minimize clock delay. In Vertex 5, there are 32 separate clock networks. In Spartan 3, there are 8 separate clock networks. These clock trees reference the BUFG CE, the BUFG clock enable, or the BUFG MUX primitives from the Xilinx Unified Library. The BUFG clock enable is designed to not only route a signal on the global, but allow a designer to actively turn the distributed clock signal off, like a clock enable, hence the name. The BUFG MUX allows designers to actively switch between two distributed clock signals driving a circuit. So for a while I could drive one, and then we could switch to the other. As I mentioned earlier, there are local clock routing resources for low fan-out clocks and SerDes clock signals. These resources need the BUFR and the BUFIO primitives respectively. Clock generation is handled by the PLL, phase lock loop, and the DCM, the digital clock manager resources. The DCM consists of 3 resources. The DLL, which is the digital delay locked loop, removes system skew between the FPGA and another external component that you may have on your board. It also has outputs that will phase shift the clock by 90, 180, or 270 degrees. There's also a divided clock output, as well as a clock multiply by 2 output. The DFS, or Digital Frequency Synthesizer block, allows you to multiply and divide the clock with greater resolution than you will get with the DLL block. With the appropriate attribute, you can multiply and divide to even generate clocks on a fractional basis of the input clock. The DPS block, or Digital Phase Shifter, affects both of the other 2 blocks, that is, the DLL and the DFS output. The Digital Phase Shifter allows for smaller degrees of phase shifting generated clock signals. The I/O translators allow different input and output thresholds on each I/O pin. Some of the supported I/O standards are shown here, such as LVTTL and LVCMOS, both with different I/O voltages. HSTL, SSTL, LVPECL, to highlight a few of the other I/O standards. The different I/O standards require separate input and output reference voltages for each I/O bank. This is an important requirement for users to anticipate because it does limit the I/O standards that can be used for the other I/O pins in the same bank. Notice in the diagram above there are 8 different banks shown. That is basically how the chip is broken down along the edges of the die. So within these 8 different banks, you can have many different I/O standards. Generally, designers put just one I/O standard within a single bank. However, each bank can support several different I/O standards in the same bank, as long as they share the same reference voltages. So designers have to take the time to verify that their I/O standards are compatible. To do this, check the necessary required voltages for your I/O standards from the device datasheet. We categorize a number of our resources as dedicated. This is because they have reserved space on the die and are already built, which means they do not use CLB logic in their construction. The first example is the clock management resources, the DCM, the PLL, and the dedicated clock trees. Note that JTAG is built right into the device. This does not use any regular FPGA resources. JTAG is built into all of Xilinx's devices. As I mentioned earlier, I/O translators, DDR registers, and SerDes resources are all dedicated in the silicon as well. Other dedicated resources include block RAM, DSP slices, gigabit transceivers, commonly called MGTs, Tri-Mode Ethernet Max, PCI cores, and in addition to those dedicated resources, the PowerPC 440 and the faster GTX transceivers are also included with the Vertex 5 FXT family of devices. Note how each of these resources is dedicated on the die. As I mentioned a moment ago, the PowerPC 440 is dedicated on the Vertex 5 FXT devices. However, there is also a soft processor core available called Microblaze. It is a simple Harvard architecture processor that has good speed and is supported on every FPGA because it is built with CLB logic. There is also available a digitally controlled termination resistance, or DCI, which is designed to save users from placing termination resistors on their board. The DCI is supported with a number of different I/O standards. So check out the datasheet to find a bit more information about the DCI. In summary, FPGAs are very flexible creatures. We have seen a number of ways that they are programmable on a feature basis, but the most significant is that they are reconfigurable logic. The benefit is that there is very little risk and cost associated with making a change to an FPGA design. They also provide a means of getting your system to market very fast. Xilinx FPGAs use LUTs instead of gates. This allows designs to pack more logic into their FPGA because each LUT can handle any combinatorial function of up to 6 inputs. Xilinx FPGAs also contain registers, carry logic, clocking resources, and dedicated muxes to improve system speed for all applications. Xilinx devices also have a variety of dedicated hardware resources including DSP Slice resources, block RAMs, PCI cores, EMAC cores, and SerDes I/O functionality that makes system speed nearly equivalent to ASIC speed. Doing a gate count comparison between an ASIC and an FPGA is very hard and never one-to-one. For example, a 0.13 micron standard cell ASIC might have 100,000 gates per square millimeter, but a Vertex 5 device has about 20,000 gates. This begs the question, why? This is actually pretty simple: programmability, which the ASIC, of course, does not support. As I mentioned earlier, FPGA makers don't give users access to all of the gates. In fact, customers don't use all of the functionality and gates built into the FPGA. Built into the device are various programmable resources that are used for routing signals and configuring the FPGA. Likewise, some of the dedicated resources, like the dedicated muxes, carry logic, etc., go unused. This takes some of the room that is available on the die and simply wastes the gates. But is this bad? No, it isn't, because the devices are designed to meet the greater needs of many hardware designers. This means that they are intentionally built with a very flexible architecture that can build both high device utilization and system speed. So don't think of it as wasting resources. Think of it as built-in design flexibility that enables you to get what you want and need out of the FPGA. So how do you complete a gate translation? Well, the first step is to separate out the various logic resources you have in your FPGA design. This means the logic, registers, RAM, cores, and the I/O resources all have to be separated because they will have a very different gate count in the FPGA. Likewise, you might need to further partition your cores into logic and RAM. Next, we'll assume that 6 to 12 gates are used per lookup table. RAM bits will be assumed to be equivalent, and up to 100 ASIC gates per I/O will be counted. Now, from these estimates, you may be asking yourself, why are so many gates wasted per IOB? Well, the reason is that each IOB can translate a signal into 40 different I/O standards. Yeah, that's a lot of flexibility built into the FPGA. And as I mentioned earlier, the more flexibility, the more gates may be wasted. We are also going to assume that 7 gates are used per register. Now, the other way to do the register gate comparison is just to simply swap the flip-flops one-to-one and not count any gates for them. So what design strategy do you think you need to use here? You probably already know this by now. To get the most out of the FPGA, you need to try to use as many of the features as possible, especially the dedicated hardware such as block RAM, DSP slices, and any dedicated cores your device has. So in our example, we have a 250,000 gate ASIC design. we'll assume this count is just for combinatorial logic, and that we need to choose an equivalent FPGA. The design uses 4 block RAMs and 243 I/O pins. The block RAMs we'll assume are equivalent, and they are. The pads equate to an equivalent number of IOBs, but of course the gate count is significantly higher since there is so much programmability. But the bottom line is we have to have an equivalent number of I/O pins for this design to map over. So given the 250,000 gate count, let's just assume the logic maps only to LUTs and that we'll ignore registers. This design would require between 20,000 and 40,000 LUTs, so you go to the datasheet for any of our devices and look for one that has enough LUTs, RAM, and I/O pins. In our case, we'll assume the design needs to target vertex 5, and after referring to the datasheet, we found that we can choose from a number of densities. To narrow the choices down, we would probably recommend that the designers synthesize for each of these devices and choose the one that fits most efficiently. However, most customers like to design around the 80% device utilization level. This makes it easier to meet your timing needs. If the design was running at low speed, say less than 150 MHz, you might be able to pack the design at higher device utilization. You should also keep in mind that no modifications have been made to the design to help it run at high speed, so further design changes will probably need to be made. We'll talk more about design changes in a little bit. So what influences gate counts? Well, obviously the coding style, the number of metal layers, the process geometry of the FPGA. A huge one, of course, is the ASIC library quality, because, of course, those libraries are very different from FPGA libraries. But also placement and routing algorithms, which will dictate the final number of programmable interconnectors used, the core contents, the I/O requirements, and any special features that are included in the design. So in conclusion, doing an exact gate count conversion is nearly impossible. Any conversion done will only be a rough estimate. Most customers just resynthesize their design and pick a device that can fit the design at about the 80% device utilization level. But at least now you have an idea how to do a simple estimate and you understand why these are only rough estimates. But the biggest takeaway we're going to make is that resynthesizing ASIC code directly into an FPGA will not use the device resources to full advantage. You'll have to instantiate resources that are not inferred, and you'll have to make sure your coding style is optimum. So first, let's take a look at just a simple example. In this case, we have built a simple 8-input AND gate. Nothing challenging at all, and this is put in any architecture. We built this in a similar way for both VHDL and Verilog. Like I said, this is very basic. So when we build this 8-input AND gate into an ASIC, we are essentially building with 2 4-input NAND gates to get a wide function. But as you know, this implementation will vary by ASIC vendor technology. You may have to build this with a wider NAND gate depending upon the ASIC vendor. When we put this into a standard cell ASIC, we get a circuit and we end up using 14 of the ASIC gates. In this technology, this component resulted in an approximate delay of 0.47 nanoseconds. Certainly good performance and built efficiently for this ASIC architecture. But beware that your ASIC libraries do not map over to an FPGA library. In fact, very wide gate types tend to infer long delay paths in FPGAs. So these types of logic will have to be optimized for an FPGA design. When this same design is resynthesized for a Xilinx FPGA, we have to keep in mind that the primary combinatorial logic resource is the LUT. In our case, we chose to target a Spartan 3 device. Spartan 3, as you may or may not know, has a 4-input LUT. So the finished design looks very much like the ASIC result. There end up being 3 LUTs used, and the component results in 2 levels of logic. While the implementation looks almost identical to the ASIC result, it is important for designers to appreciate that they do not have control of the silicon at the gate level in an FPGA like they might have at an ASIC. When synthesizing basic logic for FPGAs, designs essentially map to LUTs and registers, which are the primary building blocks. In a Spartan 3 device, the performance obtained is approximately 0.7 nanoseconds. While this is still reasonable speed, what I want to emphasize to you is that you should notice that the delay path requires 2 levels of logic. Designs that are ported to FPGA technology from an ASIC always have paths that infer multiple levels of logic. Improving these paths is sometimes a big issue with designers trying to obtain peak performance in an FPGA. That is because the LUT cannot be widened and, by its nature, is input limited. And coincidentally, all FPGAs are limited in this way. Until the FPGA industry builds a high-fin and combinatorial logic resource, this challenge will not go away. Finally, as you might expect, when we synthesized this simple design for Vertex 5, we got an even faster result. Now, a lot of people would say, well, that's because Vertex 5 is built at a better technology. Well, that is part of it, but the real question to ask yourself is, how many logic levels do I expect this code to synthesize when mapped to Vertex 5? The answer is it will synthesize to the same number of levels. Since Vertex 5 has a 6-input LUT, and the design requires 8 inputs, we will get pretty much the same result that you see here. You should also note that in this example, the FPGA did end up using a few more gates. That is pretty typical and is not a problem, unless the designer is building a lot of 2-input LUT functions, and generally synthesis tools are smart enough to avoid this kind of situation. The key lesson is that you're not using all the inputs to each LUT. You're going to waste some gates. But if you build with good HDL coding styles, you will improve your design's efficiency and speed. Now let's take this last example to the next level so you can appreciate why logic has to be optimized for an FPGA. And we're going to start by asking you a question. Based on the last example, how many 4-input LUTs would be required to implement a 32-input OR gate? So what you're going to need is some paper and to start to draw out how you think a 32-input OR gate would be synthesized with a 4-input LUT architecture. So take a little time, study the last example, and give yourself a couple minutes to evaluate the result. Likewise, once you have drawn it out, I want you to try and determine how many logic levels you think this would generate. Well, thanks for trying your best. As you can see, you should get something like this. Wow, that's a bunch of LUTs. In this case, 11 total LUTs. But note, only 3 levels of logic. This is because the second and third layers can quickly group the logic for the best result. And what is more, you can actually build a 34-input OR gate with this circuit. Do you see the 2 unused inputs on the third logic level? So for comparison purposes, we can estimate the performance if we know an approximate LUT delay and an approximate net delay. If we assume 0.3 nanoseconds delay for each net and 0.2 nanoseconds delay for each LUT, then the total estimated delay for this circuit would be about 1.2 nanoseconds in a Spartan 3 device. Recall that our last example had a delay of about half of this. That was simply due to the logic levels. Recall that circuit required 2 logic levels and had only 8 inputs. Finally, take this circuit to the next level. How do you think it would be implemented in a Vertex 5 device with a 6-input LUT? So once you draw it out, you should use 7 LUTs and 2 logic levels. Do you think it would be faster? Certainly it would. Not only because the technology of Vertex 5 is faster than Spartan 3, but because this circuit would only use 2 logic levels. That's the key. It is also important that you remember to convert any tri-state buses in your design. That is because there are no real tri-states in Xilinx's newest FPGAs. These are now implemented with LUTs and the F7 and F8 muxes. Recall that the F7 can implement an 8-to-1 mux, and the F8, when using the 2 F7 muxes as well, can implement a 16-to-1 mux. The dedicated muxes and the LUTs should be easily inferred, but it may depend on your coding style. Most designers infer a tri-state buffer by testing for the enable signal to be asserted, and if it's not, a high Z output is defined. Most synthesis tools will infer a tri-state buffer in this case. The problem is that getting the dedicated mux was primarily built to make muxes, not bidirectional buses. Historically, a case statement is usually required to infer the dedicated muxes, and sometimes a synthesis switch is required, which is usually on by default, however. So just keep in mind that you may have to convert your code to use a case statement, and this may depend on your synthesis tool. Now, we want to review some of the key points. Now, let's take a simple register-to-register circuit and evaluate its performance. So we're taking the simple circuit, the 8-input AND gate, and registering both the inputs and the outputs, as shown here in VHDL and in Verilog. And then we're resynthesizing and re-implementing the circuit. So when we do our performance comparison, we get top speed for the Vertex 5 implementation at around 550 MHz. When the same design was implemented in a 13-micron standard cell ASIC, we got significantly better speed and better gate utilization. That is pretty typical. In this case, there is really no way for the FPGA to obtain better speed. It's already at peak performance. Now, when we look at some typical high-performance design speeds, we see some other patterns. In the case of a typical design implemented in Vertex 5, we ended up synthesizing the worst-case delay path to 4 logic levels. Now, this is not necessarily a good synthesis result, but it is typical of less experienced FPGA designers. When the design was targeted to the same ASIC, the performance was about double. This is a pretty typical performance hit if the designer does not do any optimization for the FPGA. The lesson here is not so much that the FPGA design is always slower, but that it is important for the designer to optimize their HDL code for the FPGA. There is no question that simple combinatorial logic implemented in an ASIC is typically faster than an FPGA implementation. Why? Well, because the ASIC fine-grained architecture allows for wider input functions to be implemented with less delay. ASICs also have dedicated routing structure rather than the programmable routing structure you see in an FPGA. However, you should remember that critical paths typically are synchronous paths. They typically include I/O, RAM, PCI, and DSP resources. This is because Xilinx FPGAs are a cutting-edge ASIC. Since these dedicated resources are very, very fast, they often make timing critical paths equivalent to an ASIC result. While there are a number of ways to improve the performance of an FPGA design, and they can vary significantly by design, one of the most important ways to improve the speed of a sequential design is to pipeline critical data paths. In this example, we have a data path that has 2 logic levels. That means that the worst case path goes through 2 LUTs in series. To break these logic levels, we need to insert a pipeline stage. A pipeline stage is just a bank of registers to break up the data path. This may require a significant number of registers depending on the number of bits in the data path and the number of logic levels that need to be reduced. Well, as you can imagine, it is more likely that you will have to pipeline Spartan 3 designs than Vertex 5 designs, because Vertex 5 has a 6-input LUT and is more likely to handle higher fan-in combinatorial functions more effectively. This, of course, means that pipelining any FPGA that has a 4-input LUT is a prime concern. But you will still have to consider pipelining critical paths in Vertex 5, depending on your timing objectives, even though this technique will increase your design size. Now, incidentally, pipelining has been so essential for gaining speed in FPGAs that every LUT in FPGA has an associated register with minimal routing delay. This also explains why the logic cell is the preeminent benchmark for device density. So keep in mind that you should always evaluate your worst-case timing path with either your synthesis tool, that is your schematic viewer and the use of timing constraints, or by evaluating your timing with the Xilinx Timing Analyzer utility that is included with the ISE design suite. And if you need to add registers, consider pipelining the outputs of a purely combinatorial path or the outputs of a hierarchical boundary. In the end, these techniques are the simplest way to make an effective design change to improve the speed of your design. Timing constraints are added by designers with their synthesis tool or with the Xilinx constraints editor. They are the primary means of communicating your performance objectives with the implementation tools. That is the common name for the ISC design suite. With timing constraints, the tools try to manipulate the placement of logic so that a routing solution can be found that meets all of your timing needs. This is simply not possible by hand, and controlling the layout of the design is much harder and requires more effort than you might think. In fact, manually controlling the layout is extremely rare in the FPGA world. Realistically, you might at some point in the future wish to try to floor plan design by making area constraints, but this is only recommended to our most experienced designers. Timing constraints include globals, which cover almost all your design's delay paths. These constraints include the period for internal delay paths, the offset in, which covers your input paths, and the offset out constraint, which covers your output paths. Path-specific constraints are also frequently used to cover multi-cycle paths, which are created when a designer builds with clock enables. This entire topic is introduced in the Fundamentals of FPGA Design course and is completed in the Designing for Performance course. Better coding styles mean limiting the number of logic levels inferred between register resources. The whole process requires you to be familiar with your synthesis tool, since most designers use timing constraints and their synthesis tool schematic viewer to evaluate their HDL code performance before they even complete one implementation. So don't waste your time. Put forth the effort to evaluate your HDL code and listen to the coding techniques RELs so you can fix your design before you even get to place and route. We want you to be successful, and the most likely work you will eventually have to complete is to fix your coding style. How to build a reliable FPGA design is actually a simple question. The first step is to design synchronously. How this is implemented has a number of factors to be considered, but the bottom line is if you have ever had a design that had a sporadic problem, you may have been a victim of your own poor design techniques. If you design synchronously, your FPGA will operate at any frequency that meets your system timing. The key is to be aware that all FPGA makers have lot variations. This means that your part will be at least as fast as the speed grade you purchased. I have also seen cases where customers will try to change their internal delays to meet an asynchronous design problem, with the hope this will get the design to work. It may work for a while, but there is no telling how long it will last. So the simple rule is don't expect timing constraints to fix your asynchronous design problem. Build the design properly and it will work. Let's have a look at some of the synchronous design methodologies. FPGA designs should have as few clocks as possible. This just makes the design simpler and saves global routing resources. Of course, most designs have several clocks, but always try to reduce the number of clocks if you can. Likewise, try to use one edge of the clock if possible. This is for the same reason as having one clock. Now, D-type flip-flops are not so much a requirement as a suggestion. When you use the D-type flops, this reduces the combinatorial logic on your data paths since the D flip-flops were already built into the FPGA. Registering the inputs and outputs of each block enables effective timing estimation when pipelining. Likewise, this is the easiest form of pipelining a design. To reduce the number of clocks, you should consider building with clock enables. This will save global clock resources and ensure design reliability. Registering inputs and registering asynchronous signals is important as well. If the clocks are unrelated, try to avoid metastability problems by using a synchronization circuit. Likewise, don't gate, derive, or divide clocks manually. Use a DCM or a PLL resource for that purpose. Or build it with a clock enable. Derive clocks with LUTs and registers almost always builds a glitch into the system. Likewise, don't use asynchronous sets or asynchronous resets, especially in Vertex 5. Try to keep in mind that global resets are not necessary since the FPGA will power up in a known state. following these tips may seem like more work, but remember that you are really going to be saving time from debugging your design later if it ends up glitching. If it does not glitch, you may be saving time from having to fix your finished product after the fact. In summary, don't worry too much about gate counting methodologies. Again, they're only a rough estimate. It is very important, of course, to optimize your HDL coding style, and of course, instantiating Xilinx dedicated hardware resources into your design improves your system speed and maximizes the amount of logic you can pack into the FPGA. One of the primary means of improving the speed of your design is to pipeline your timing critical paths. So make sure that you evaluate your timing critical paths at the synthesis level with your synthesis tool schematic viewer, and perhaps consider pipelining these timing critical paths early in the design process. Use timing constraints because they're a primary means for improving your system speed during the implementation or the place and route process. Lastly, get your design to work properly the first time by always designing synchronously. And again, this topic, as well as all of these topics, are covered in numerous places in the Fundamentals and the Designing for Performance courses. Well, there are lots of places to learn more about FPGAs, and they all start at support.xilinx.com. To this point, you should probably already have had a look at your chosen device datasheet. These resources cover everything you might need to know about the specific device. From configuration to packaging, from device offerings to specific features. If you have not seen your datasheet, it is of primary importance that you do so. They can be easily found at our website. But I want to take a moment and point out some other resources at support.xilinx.com you may find useful. One of the best resources is the Answers browser. This is primarily a resource for looking up a technical issue or a bug you might have found with the software. If so, enter some of the keywords found in the error message. This will often lead you right to the technical solution, if one exists. You can always feel free to call our hotline, but keep in mind that the solutions logged here are pretty much the same answers you're going to get on the phone, so I'd recommend trying the solution listed here first. Another use of this tool is to enter in keywords like timing constraints or pipelining to learn more about these resources. The Answers browser will point you to a primary resource such as an application note if one exists. But still, if it has to do with learning the functionality of our tools and devices, a lot of what is necessary to be successful is taught in one of our courses. So don't be reluctant to go to the customer education website, even though I've already mentioned that once before.